In this video, we're going to review one example of all integer optimization problem. We're going to go through the details of the problem. We're going to formulate the LP model, and then we're going to solve the LP relaxation. And we're going to round the solution of the LP relaxation to the nearest integer solution. And we're going to see that it's not going to be the best optimal solution, even for small scale problems like this. Ultimately, we're going to solve the integer LP using Excel solver. So here I have the question. So this is the problem. We have a real estate company. They have a limited budget of $2 million and they want to use it for purchasing new rental properties. They are looking into townhouses as well as apartment buildings. So each townhouse can be purchased at a price of $282,000, and they have a constraints here. They can't buy more than 5 townhouses. Apartments, on the other hand, they can buy them at a price of 400,000, and then there is no limit on the number of apartments that they can purchase. There is a constraint here. They have the management has a maximum of 140 hours per month that they can allocate to these properties, to the new properties that they're gonna buy. Each townhouse is expected to require 4 hours per month. However, apartment buildings are expected to require 40 hours per month. Each apartment, 40 hours per month. So annual cash flow that they expect to get 10,000 per each townhouse, 15,000 per each apartment buildings, right? So obviously apartment buildings are more favorable because at the end of the day, they want to maximize the cash flow. All right. So, and then these numbers are after deducting mortgage payment and operating expenses. So these are net cash flow that they expect to get. So the question and the decision that they have to make is that how many townhouses and how many apartment buildings to purchase in order to maximize their annual cash flow. So as you can see, the nature of the decision variable, we have countable number of townhouses and apartments. And here the difference is huge between one apartment and 2 apartments, for example. If you solve LP relaxation and get, let's say, 1.5, it's really tough. You don't know whether you're gonna round it down or round it up, right? And this is something that we're gonna look into that in this question. The notion of rounding, that it may not be guaranteed to give you the best optimal solution. So let me move on. So in terms of the formulation, decision variables are going to be the number of townhouses and number of apartment buildings. Let's denote them by T and A, capital T and capital A. So the objective function is to maximize the cash flow. We said 10,000 per each townhouse, 15,000 per each apartment. And then the constraints that they have a limited budget. They have a limited time of management per month. And we also had a limitation on the number of townhouses that they could buy in the beginning of their investment period, right? The next slide, in terms of the decision variables, we know that they can't be negative. And also, you can't buy a fractional number of townhouses or apartments. So this is really a case of all integer linear programming, because we have 2 decision variables. Both of them have to take only integer values. So now I'm going to go into Excel and we're going to try we're going to try to solve this problem using the LP solver, and we're going to see whether it's going to lead to the best solution. So this is the formulation of the problem. We want to maximize the cash flow, and then we had 3 constraints. So I'm going to go ahead and create a spreadsheet model. So decision variables. We have townhouses, and then we had apartments. So 2 decision variables. All right. So, and then objective function. It's going to be 10 times townhouse plus 15 times apartments. Next thing would be the constraints. We had budget. We had manager limitation, and then we had max max available townhouse. So the budget, the left-hand side would be 282 times the number of townhouses plus 400 times the number of apartments. So the left-hand side should be less than or equal to 2,000. So all numbers are in 1,000 actually. This was 2 million and we are factoring 1,000. So the number here is $2,000. So the manager time 4 times number of townhouses plus 40 times the number of apartments. And that should be less than or equal to 140. And then we know that the townhouse, the number of townhouses should be less than or equal to 5. All right. So this is the spreadsheet model. We have an integer constraint for both of our decision variables. If we go ahead and solve the LP relaxation, so LP relaxation is actually the problem without the integer constraints. So basically you allow, or without the integer assumption of the decision variables, right? So you are relaxing the notion of the decision variables being integer and having to take integer values, right? So if we just relax that, if we just remove that, it's this simple LP problem that we know from chapter 11. We already know how to solve this. So if we want to go ahead and solve this, we can go ahead, go to the solver, data tab, Excel solver, and then if we maximize the objective function, the cash flow by changing these 2 decision variables, townhouses and the number of townhouses and the number of apartments to be bought, subject to these 3 constraints. Left-hand sides less than or equal to the right hand side and solving it through simplex LP method. And that's it. So you see, I have the non-negativity constraints, but I don't have anywhere I haven't defined the integer constraints or integer assumption of the decision variables anywhere on my solver. So if I solve this, this is actually the LP relaxation. The solution that is going to pop up here, it's going to be the answer to the LP relaxation. So let's go ahead and solve it. So I'm okay with this. So you see here, I just solved the LP relaxation. I didn't force these two to be integer. So this is the optimal answer for the LP relaxation. So let me just copy that. So this is for the LP relaxation. But then, of course, you can't have 2 point, let's say 5. Let's just uh, I mean, round it up a little bit. It's like 2.5, and this is 3.25 of apartments, 2.5 of townhouse. You can't have a fractional. You can't purchase a fraction of a townhouse. You can't purchase a fraction of an apartment. So you have to really go with a whole number. So, but usually in practice, especially when you have large scale problem, it's much easier and it's much faster to solve an LP. You can use simplex method, and it's going to be it can be solved within seconds or minutes. But then when you add the integer constraints, especially if you're working with a large scale problems, it's going to take a lot of times, and it's going to take a lot of efforts. It's going to need new methods for solving it. But in practice, usually they go first with the LP relaxation, find the answer, and then round the solution. So if we want to round these solutions, so I would go ahead and rounded alternatives. So rounded alternatives. So like I said, these two numbers are impossible to be our best answers. But we can play with these two numbers, round them down, round both of them down, round both of them up, round one of them down and the other one up, round one of them up and the other one down. So these are 4 different answers that we just found using rounding either up or down of these decision variables, optimal decision variables, optimal for the LP relaxation problem, not necessarily for our integer problem. And let's see which one of these 4 are going to be feasible and what is going to be our objective function. So I'm going to uh, put townhouse apartments here, and then we check to see if they are feasible and what is the cash flow. So let's go ahead and check those 4 solutions. So let's say 2 and 3. What I'm going to do, I'm going to copy them from here and paste them in here. So since I have all these formulas here, it's going to check to see if they're feasible, and it's going to give me the cash flow. So let's go ahead, go one by one, 2 and 3, copy and paste only the numbers. So the cash flow is going to be 65, which is definitely less than my original value of 73. All right. And I can see that all my constraints are satisfied. So it's below the budget. The manager is not spending more than 140 of its limitation. It had a maximum of 140, but it's using 128. And then we're only buying two, which is definitely less than five. So it is feasible with a cash flow of 65. Next answer, 3 and 4. Its objective function is 90. The cash flow, is it feasible? No. And we are violating both budget and manager time constraints. So these two are violated if we go with 3 and 4. All right. So let's check the next alternative. 2 and 4, it's going to lead to a cash flow of 80 if possible, but still we are violating 2 out of 3 constraints. So it's, again, it's not feasible. And then for the last alternative, 3 and 3, the cash flow is going to be 75. And then again, it is not feasible. As you can see, the budget constraints is not satisfied. So we're spending more than what we had available. So none of these last three are feasible. The only one that is feasible is going to be this one. All right. 2 and 3, which is basically rounding down both of the decision variables. But let's just check to see what is the optimal solution. Before that, let's take a look at the feasible region of the LP relaxation problem of this one. We already know how to draw the feasible region when we have only two decision variables, right? So we can draw each constraint as a line that divides the space into two half space. So if we have all these constraints, we had 3 constraints, and these are the ones. So the intersection of all these half of spaces would be these shaded area. But then we are only looking at, if we only interested in integer values, as you can see, out of this continuous region, only these we have 6, 6, 12, and 5, 17, and 3, 20 points, only 20 points out of these region, continuous region, which contains infinite number of points within it, right? Only 20 of them are gonna be feasible, are gonna be actually in the feasible region if we add the integer constraint. Right? So no point between these two dots are going to be acceptable. Only one of these dots are going to be acceptable or are going to be feasible with the assumption of integer assumption for the decision variable. But when it comes to integer problems, there are multiple solving methods. But at the end of the day, all of them are trying to find a replacement for our original convex hull, this whole thing, for the feasible region of the LP relaxation. They're trying to find a replacement that is still convex and has all the corners to be defined as an integer value. You see here, this corner is an integer value. Instead of going up all the way to here, if we just cut it right here, which is an integer value, this would be a feasible solution for our integer ILP, and then bring it up to here, and then here and here. So we are basically cutting these region from the feasible region of the original or LP relaxation problem, right? This new convex region is called convex hull, which again, it's going to get too technical, but at the end of the day, if you have this one, the convex hull, you can use you can basically add these new constraints to the model and use the uh, use your problem, you actually solve your problem using the simplex method, because we know that using simplex method is going to give us a solution, an optimal solution in one of the corners. And if you can manage to have your convex hull defined only on these corners, when you solve this, it's going to definitely give you one of these corners that is going to be appropriate, that is going to be actually feasible in terms of your integer constraint, right? So moving back to our model, but that was just for your information. You just need to know that it's going to be limited, much limited when you have integer constraints, when you have integer assumption for your decision variables compared to LP relaxation. And then you also need to, it's great to know the concept of the convex hull, which is a smaller feasible region that only contains corners, extreme points that are integer, that are actually feasible in terms of our integer constraint. So moving back to our model, now let's go ahead and find the actual optimal solution having these integer constraint and see if it's the same as what we had here using the rounding technique. So I'm going to go back to my solver, and this is how we add the integer constraint. So if you go back to the solver, the way you define the integer assumption for your decision variable is by adding a constraint, an integer constraint. So I'm going to add, I want these two decision variables to be integer. All right. So, and remember, so far we have been working with less than or equal, equal, greater than or equal in uh, linear programming problems. Now we have three more: integer, and it adds the word integer after you pick int; binary. So we defined integer. We have we know integer values are the countable numbers, that they can only take whole numbers. Binary, those decision variables can only take 0 or 1. And then there's a last one, different or all different, that actually is a very, very specific, very special type of decision variable. It actually it gives you a numeration from, let's say, 1 to an integer number. So let's say if you have 3 decision variables, in this case, if you have 2 decision variables, by this one, you force them to be 1 and 2. All right. If you had 10 decision variables and you pick all different, they're going to be, they have to take values from 1 to 10, and all of them should be different. And that's usually good for sequencing type of problems, when you want to actually put them in different orders, right? So that's a very specific type, and we're not going to be dealing with this one, but make sure to check to set these two decision variables to integer, add, and that's it. So I have it here into my set of constraints, and everything else the same. So now if I solve it, one thing that we just need to be careful is that when you have integer or binary type of constraints, there won't be any sensitivity report anymore. So if you want to run, if you want to do a sensitivity analysis on a binary or on integer LP, you have to do it manually. You won't be able to use sensitivity report from the Excel. All right. Okay. So the optimal solution is buying 4 townhouses and 2 apartments. And if you do that, you're going to get a cash flow of $70, 70,000 actually. All these numbers are in thousand. And none of your constraints are violated, as you can see here. And what we see here is that it's definitely is different from what we found using the rounding trial and error techniques. We couldn't find 4 and 2. So basically, it tells us that this is not guaranteed to give you the optimal solution.